Thanks for organizing this nice workshop, and thanks for the invite. So what I wanted to talk about is it's based on mostly two recent works. So one is with Kusuoka, the son, and his PhD student Nagoji. And the other one is with James Coe, who is a PhD student of Leonardo Tolomeo from Edinburgh. And the general question is, if you take an SPDE and you look at the invariant measure, so the kind of SPDEs that we're going to look at, let me write a sort of general form. So let's make them scalar valued. And so this is just to sort of try to understand how the power counting works, right? So I allow myself to replace the Laplacian by a power of the Laplacian, right? So this is really just Laplacian to the power gamma. Of course, the interesting case is gamma equal 1, where it's the normal Laplacian. Then we have some form of nonlinearity. And the two examples that we're going to be most interested in is when this is either like the Navier-Stokes equations, so then this would be the Navier-Stokes or the Euler nonlinearity, or when we look at these 5-4 models, and then this would just be u cubed or minus u cubed. Okay? And then we take a noise, and we always look at noise which is sort of white in time and correlated in space. So psi is space-time white noise, and then you stick some possibly negative power of the gradient. So you could have alpha equal to 0, then it's just space-time white noise, okay? Or you can have some other values of alpha. I mean, alpha could be negative, right? And then it's kind of worse than space-time white noise. That's also fine. And the question is that, well, so suppose you have an invariant measure, right? So you have an invariant measure. Let's call it mu. And then the question is, what's the sort of things that you can say about mu? So can you say things about, regularity of mu, or can you say at least something about almost sure properties of mu or something like that? Okay, so that's kind of the question. And especially in cases where you don't, just have a formula for mu. Okay. And so more precisely, what's the sort of thing that you can ask yourself? Well, one question you can ask yourself is, does the presence of the nonlinearity affect the almost sure properties of mu? Okay. In other words, if you compare to the invariant measure, so let me say, let's see, dt, whatever, I'm going to need v and w, so I need some other letter, whatever, z, well, z, so that's what D'Aprato and Zapchik always use. So z would be the linearized equation, so that one has an invariant measure mu naught, which is just Gaussian, and everything is explicit, and so that one, everything, you can answer pretty much any question you care to ask about the invariant measure of that guy. And so then you can ask yourself, one question you can ask yourself is, under what condition is mu equivalent in the sense of measures to mu naught? Okay? So that means that they have the same almost sure sets, right? The same measure one sets. They're in the same measure class, so they have a density with respect to each other. So that's, in some sense, it's one infinite dimensional analog of somehow the measure having like a smooth density, right? Like you need a reference measure. There's no Lebesgue measure, so the only natural reference measure that you've got here is that one, right? Or at least the only natural reference measure that you can describe explicitly. There's another notion of smoothness that you have. So in finite dimensions, the following two statements are equivalent. Okay, so suppose in finite dimension, take mu naught the Lebesgue measure. Okay, And then the statement mu is equivalent to mu naught. So that statement here is equivalent in finite dimensions to the statement that mu is equivalent to all translates of itself. Okay, so what does that mean? So it means you take, say, T psi is the map that maps u to u plus psi, right? So that's translation by psi, okay? And then the question you can ask is it the case that if I push forward the measure mu under T psi, the new measure is still equivalent to mu? Okay? Say for some dense set of psi's, so typically, say smooth, right? For all psi in C infinity or something. Okay, so in the sense, like, you take the measure, you shift it by a smooth function, so the new measure you get still equivalent to the old one. So in finite dimensions, if this is Lebesgue measure in Rn, and this is just all shifts in Rn, these two statements are equivalent. Okay? In infinite dimensions, there's no reason for them to be. I mean, they're clearly not equivalent, because if I take that measure here and I take the measure that's blown up by a factor 2, then these two measures are mutually singular, but both of them have that same property. So this is kind of a weaker property, right? Like if this is true, then clearly this is true as well, because the Gaussian measure has this property by Cameron-Martin. Okay? So this is a weaker statement than this one. And then if we're talking about sort of strength of statements, there's another question you can ask yourself. So this sort of seems like it comes out of nowhere, but it actually has some motivation. And that's sort of the QFT bit in the title of the talk. So there's something called Siegel's axioms, which sort of he came up. So Siegel, it's Graham Siegel, so the guy from Oxford. So he came up with these axioms sort of in the context of trying to formalize topological quantum field theory in a sort of pure mathematical way. So for him, a field theory is like a functor on a cobordism or something. But if you actually take the fancy words and you translate them into what they actually mean, it basically says something like you take somehow, say, you take manifolds, for example, like the three-dimensional version would be that you have sort of three manifolds with boundaries and you can kind of glue them together along the boundary to form kind of larger three manifolds. So if you do a two-dimensional picture, so this would be a two-dimensional manifold with boundary, right? And then this would be another two-dimensional manifold with boundary. And then here you can sort of glue them together to make one surface, right? And then what you can do is you look at a quantum field theory here, and then you sort of have boundary data for these quantum field theories, and you glue them together along the boundary data, and then there should be some consistency condition between these constructions, okay? And you can, if you want, you can kind of reinterpret this in terms of somehow invariant measures for these phi-4 equations on these manifolds, and then with boundary data and gluing together the boundary data in a certain way. And that was actually recently done. So there's a very recent paper or preprint on arXiv by Trish Gunaratnam, that's the correct way of pronouncing his name, and Nikolai Barashkov, where they do it in the case where these manifolds are just tori, right? So you sort of take tori and you sort of glue, or basically cylinders, pieces of cylinder, and you sort of glue cylinders together to make a larger cylinder, so then at least you don't have any problem with curvatures and metrics being compatible or anything like that. And in that case, they were able to somehow validate Siegel's kind of abstract picture in the case of phi-4. And so there, what do you want to, so for this glue, okay, so why am I telling this whole story? Is because for this whole gluing procedure, you would want to know that if you want the measure on the boundary that you get here is at least equivalent to the measure on the boundary you get here, because then you can sort of talk about amplitudes, which are sort of the densities with respect to some kind of reference measure or something. And so what this then kind of translates to is the question, if you take the phi-4 model, so the one where f of u is minus u cubed, and you do it on a 3-manifold, say 3-dimensional torus, but it could be an actual manifold, and then you take the invariant measure of that, and then you restrict the invariant measure on a 2-manifold, right? So you have a 2-dimensional surface that sits in your 3-dimensional manifold, which I think of as the boundary. But okay, you think boundary doesn't really sit inside the manifold. In fact, there's a construction here where you can build these things by doubling up, by taking 2 copies of these things and sort of gluing them across their own boundaries, and then you have a manifold that has no boundary anymore, and the boundaries of the original one are now 2-dimensional surfaces that sit inside this manifold that has no boundary, okay? So you do that construction, you do the phi-4 on that kind of 3-dimensional manifold, and then you restrict yourself to these 2-dimensional surfaces, which are really the boundaries of the actual manifold you're interested in. And then you ask yourself, well, does the law, or does the measure class of that restriction depend on the shape of the 3-dimensional thing that my 2-dimensional surface sits in, right? In the sense that if here I have the same, so this is kind of the same surface as that, okay? So that one is kind of isometric to that, but this 3-dimensional, but everything is 1 dimension more. So this 3-dimensional manifold here is not the same as this one, obviously, right? And so then the question is, if I take 2 copies of this manifold and I glue them across boundaries, I take phi-4 invariant measure on that and I restrict to this, is the measure I get equivalent to if I do the same thing here and I restrict to this, right? So in other words, if I take the restriction of mu to say a lower dimensional manifold, is that equivalent to the restriction of mu naught to a low dimensional manifold? Well, that's a different question, right? So here we're not asking about equivalence to mu naught, we're asking about equivalence between 2 things. And that in some sense is, in a way, it's closer to this kind of question, right? Because you would expect these things, like the effect of what happens here, you would expect this to be a little bit like some kind of a smooth random shift, or at least more regular kind of random shift to what happens here. So in some sense, the question is a little bit like this question, except that you first restrict to a submanifold, okay? And then again, somehow, if you know this, then of course it's true for the restrictions, but it's not necessarily the other way around, right? So it's again kind of a weaker condition, which might be easier to check. Yeah? Okay. And then the other motivation, right, so that was one of the motivations for why to look at these kind of questions for phi-4. And then if you take fluids, right, so if you take Navier-Stokes here, well, then there's a 2005 paper by Jonathan with his postdoc at the time, Tufik Sweden, where they showed that if you take Navier-Stokes exactly like this, and then you ask yourself whether you have this equivalence to the Gaussian, then they could answer this positively, so in the sense that you do have equivalence, if gamma is bigger than 1, strictly bigger than 1, which is kind of annoying because what you want is gamma equal to 1, right? So you can do it for every gamma strictly bigger than 1, but their proof breaks down exactly at gamma equal to 1, right? And so then, for a long time, people were wondering, like, is the proof sharp or is it not sharp, right? So there's certainly, you can come up with easy heuristic arguments which tell you that that boundary is sort of sharp, should be kind of sharp. But then still, even if the boundary is sharp, it's not completely clear whether the boundary value falls one way or the other, right? And in fact, in that paper with Kusoka and Nagoji, we show that generically that boundary is sharp. But then what we show in the paper with Coe and Tolomeo is that for the case of Navier-Stokes, it's actually not, right? So generically the boundary is sharp, so in the sense that if you replace this by u cubed. So if you take the phi-4 models and you do exactly the proof of, Jonathan and Tufik, you adapt the proof to phi-4, then you get, a threshold in terms of gamma, alpha, and the dimension of the underlying space. And in the paper with Kusoka and Nagoshi, we show that this is exactly the right threshold. So in the sense that if you're on one side of the threshold, then these measures are equivalent. On the other side of the threshold, they're mutually singular. And on the threshold, they're actually mutually singular. Okay, so there we have a full characterization. But the proof relies on basically not having any spurious cancellations, right? So it relies on some quantity that looks like it should diverge, actually diverging, right? And in the case of Navier-Stokes, basically by symmetry of the nonlinearity, it turns out that that quantity happens to be zero. It's a little bit like in Arnaud's paper with Da Prato, when they kind of construct the solution to 2D Navier-Stokes with space-time white noise. So it would be the case gamma equal 1, alpha equals 0 here. They kind of use some property of the nonlinearity to say that actually it looks like it would need randomization, but actually it doesn't, right? So it's a kind of similar type of property. And so then what we show in this paper is that actually the answer to this question is yes in the case of Navier-Stokes. And in fact, you can even go down in gamma, and we can go down all the way to 2/3. Okay? So in the case of Navier-Stokes, so mu equivalent to mu naught if gamma is bigger than 2/3. And then there's a condition on alpha, but the condition on alpha is really just somehow to make sure that you have enough regularity. So if gamma is equal to 1 in the case of the actual Navier-Stokes, we really just need alpha positive. Okay, so we can do anything slightly better than space-time white noise. And in the case of space-time white noise, well, we know by Arnaud and Da Prato's paper that, well, here, in fact, the answer is still yes, and it's even more than that, is that these two measures are actually equal. Okay? But that's a very special thing, because if you take gamma equal 1 and alpha equals 0, then formally, right, the invariant measure for this equation here is sort of the Gaussian free field, which if you formally write it down is sort of e to the minus h1 norm square of u, and the nonlinearity preserves the h1 norm. Okay, and that's very special to the case gamma equal 1 and alpha equals 0, and very special to 2D Navier-Stokes, because 3D Navier-Stokes does not preserve the h1 norm, but 2D does. Okay. Right, so in gamma equal 1, we have yes for every alpha positive, and for gamma, well, between 1 and 2/3, we need to assume that alpha is bigger than 3 minus 2 gamma. But this is really, so the reason we need to assume these things, it's sort of for silly reasons. It's basically that otherwise we don't even know how to prove that there is an invariant measure. Because you see, here, at alpha equal to 0, it becomes surprisingly hard to show that you actually have global solutions. Well, so again, in that paper of Arnaud with Da Prato, you can show it because you know what the invariant measure is. But if you didn't know what the invariant measure was, then it would be very hard to show that you have global solutions because you don't have, because the L2 norm is not finite for the solutions, and the H1 norm is not finite, and that's the only thing that you've got to control solutions, right? And so this alpha bigger than 0 guarantees that the L2 norm is finite, and so you can kind of control solutions. And here, when gamma is less than 1, the point is that for 2D Navier-Stokes, the L2 norm is scaling critical for 2D Navier-Stokes. So if you take the actual Navier-Stokes, so the one with gamma equal 1, then if you control the L2 norm, that's good enough to sort of control the solutions. But if gamma is less than 1, then controlling the L2 norm is sort of useless. You really need to control the H1 norm. And then that's why we need larger values of gamma. So this basically guarantees that the H1 norm is finite, or it's a little bit better than that. But it sort of guarantees that we can get a priori bounds on the H1 norm of the solution, which then allows us to show that you have global well-posedness. Okay. Okay. Yeah, are there any questions? No, okay. Right, so that's the result with James and Leonardo. And okay, so let me now try to give you some heuristic of what you expect in general, right? Oh, you cannot do both at the same time. Okay, so let's do a general heuristic. So what do you actually expect, right? Well, so first, what's the regularity of Z, right? So the regularity of Z, if you do the calculate, right? So you ask yourself what's like the best kind of function space that Z lives in. You basically find, you know, in the sense that for Brownian motion, the best space is kind of C1/2. Of course, it doesn't live in C1/2, but it lives in all the C alpha spaces for alpha less than a half, right? So there I don't put the minuses everywhere because otherwise, you know, there's minuses everywhere somehow. Okay, so the regularity of Z, you can find that it's basically alpha plus gamma minus D over 2. Okay, so that's just the calculation, okay, in the sense that it lives in every Hölder space with exponent less than that. And that's kind of optimal, and it does not live in the Hölder space with exactly that exponent. Okay? And so what this tells you is that the Cameron-Martin space for the law of Z of t is basically H gamma plus alpha. Okay, you can kind of see that because if you're in dimension D, then white noise in dimension D has regularity minus D over 2, and white noise has Cameron-Martin space L2, okay? And then if you shift by a certain amount, well, the Cameron-Martin space shifts by the same amount, and the Cameron-Martin space is always an L2 kind of Sobolev space. So the Cameron-Martin space is H gamma plus alpha. So that's the Cameron-Martin space, not of Z as a process, but just of the law at fixed time. Right, so you take Z at time 1, and it doesn't matter what's the initial data, they're all equivalent because they just differ by a smooth shift. So you take the law of Z at any fixed time, and then that has this regularity, which corresponds to this Cameron-Martin space, right? So that means that the law of Z of t is invariant under shifts, is quasi-invariant under shifts by a function which has that regularity, right? And if you try to shift it by something which has less regularity than that, then generically you'd expect to get something which is singular, what you started from, right? And so then, well, suppose that the regularity of f of u, well, the regularity of f of u now sort of depends on, you know, what f is, okay? So let's just give it a name. So typically it's going to depend on alpha, gamma, and d, but it also depends on what f is. So let's just give it a name, right, beta. And then beta, one can figure out what it is for different examples. It's not difficult to figure out. And so then, what is the regularity of the shift? So what do I mean by this? It means, well, you know, I write this equation in mild form, okay? So if I write this equation in mild form, then that basically means that u is equal to z plus the convolution of f of u with the heat kernel, or not the heat kernel, but the, the semigroup generated by this Laplacian to the gamma, right? So now if you convolve with the heat kernel, you gain sort of 2 degrees of regularity. So if you convolve with that 2 gamma heat kernel, you gain 2 gamma degrees of regularity, right? So if you look at, so this shift is sort of the integral of e to the minus 2 gamma t minus s f of u of s ds, say 0 to t, right? So if you look at the regularity of this, so that's the term that encodes the nonlinearity in the mild formulation, right? So now the solution to the nonlinear equation is basically the solution to the linear equation plus this shift, okay? So it's natural to expect that the two are equivalent, well, if and only if that shift belongs to that space, right? Now, of course, that's not a theorem, right? Because it's a theorem if the shift is deterministic, and that shift is very much non-deterministic. And it's also kind of a theorem if you have Gaussian, so but then you need the structure of things being adapted and whatever, and here we're just talking about measures on space only, right? But still, it gives you at least a heuristic of what you're aiming for, right? So now the regularity of that thing is going to be beta plus 2 gamma, right? And so therefore, the natural condition, so the natural conjecture is that mu should be equivalent to mu naught if and only if beta plus 2 gamma is strictly bigger than gamma plus alpha. Okay, and why strictly bigger? Because if they're equal, then, again, if you look at the sort of, do the analogy with Brownian motion, in the case of Brownian motion, this d would be 1, the regularity is a half, right? That means that this whole thing would be 1, so you get 1 minus a half, which is a half, and then here you get h1, okay? So that's consistent, but in the case of Brownian motion, like the Cameron-Martin space is genuinely h1, but the actual regularity that you have is not a half, it's slightly below a half, right? And so that's why at the boundary case, you'd expect that things are actually singular, because that would be the case where, it's like sort of having something which just about not C1, well, that's also just about not going to be in H1, typically, okay? So that's why that's sort of the conjecture. Okay? And so now what does this conjecture tell you? So first, okay. So first the conjecture in the case of Navier-Stokes. So here we take, so in the case of Navier-Stokes, we take alpha, right, it's bigger than something. So you can just as well think of alpha as being, a million or something, right? So there's nothing singular about what we're looking at in the case of Navier-Stokes. So we're looking at things that are actually quite regular. So this regularity is going to be positive in the case of Navier-Stokes. So gamma would be 1, d is 2, so this is actually 0, so the regularity is actually alpha. Okay. So the regularity of the solutions is alpha in the case of Navier-Stokes. So here, the regularity of Z is alpha. And so then the regularity of F, well, F is U grad U, okay? So if U is C alpha, then grad U is C alpha minus 1, and U grad U is still C alpha minus 1, right? So that would be alpha minus 1. Okay, so beta is alpha minus 1 in the case of 2D Navier-Stokes. So that's 2D Navier-Stokes. Right, so then the conjecture is, well, alpha minus 1 plus 2 gamma would need to be bigger than gamma plus alpha. So the first thing you see is that the alphas cancel out, which is kind of nice. And then you put the gamma here, the 1 here, and then so that tells you that gamma is strictly bigger than 1, which was the result of Jonathan and Tufik. Okay? So that suggests that if you take the actual Navier-Stokes, the measures would actually be singular. Right? So if they're regular, that means there's a miracle happening somewhere. Okay? So you have to find what the miracle is. In the case of phi 4, so let's do the conjecture. So the conjecture in the case of phi 4. And so in the case of phi 4, we're actually interested in the situation where you have randomization. Because, I mean, that's somehow the interesting cases from the point of view of quantum field theory. And so then we put ourselves in the case where that regularity is negative. Right? So then we have sort of, so we have alpha plus gamma minus d over 2, which we're going to assume negative. Okay, but we're just going to consider, alphas and gammas so that this is negative. Okay? And we assume that it's big enough so that at least you can renormalize things and there are local solutions somehow, right? Or global solutions. And that we're not going to sort of go into details, but now it's very well understood. So you basically, there's another condition here. It needs to be bigger than something. Basically, it needs to be bigger than minus, I guess, d plus 2 divided by 6 or something like that. So there's some condition along those lines under which, you can actually renormalize the thing. Maybe it's not, maybe it's that, maybe the alpha still should, I don't know. There's some lower bound that you can also find out by some other kind of power counting argument that tells you whether there's any chance at all that you have a notion of local solution for these things. Okay, so we put ourselves in that regime. So then what's the regularity of f? So now f of u is minus u cubed, okay, or constant times u minus u cubed. And so now u has negative regularity, right? So u cubed in principle is not even well defined, but okay, you need to do this whole randomization business so you can kind of define it. And then what's the regularity of u cubed? Well, it's not the regularity of u, but it's actually worse, right? So because you can think of, like a prototypical thing of regularity, say minus a half, is something like the map that maps x into x minus x naught to the power minus a half. So it's something that has a minus a half singularity. And if you take that to the power 3, then it has a minus 3/2 singularity, right? So taking the cube of something with negative regularity basically multiplies the regularity by 3. But since it's negative, multiplying it by 3 makes it worse, not better, okay? So the regularity of f, beta, would be 3 times alpha plus gamma minus d over 2, okay? And so then, well, so what do we want? So then the conjecture is that mu is equivalent to mu naught if and only if, well, 3 alpha plus 3 gamma minus 3d over 2 plus 2 gamma is bigger than gamma plus alpha. Right, so now we can kind of cancel out the gammas, so it's what? So it's 4 gamma plus 2 alpha is bigger than 3d over 2. Is that what I had? Yes. Okay, so you get a condition like this. And so in the case of phi 4, we have a theorem which says that this is a theorem. Okay. So there, the heuristic gives you exactly the right answer, including the boundary case. Right? So you have exactly this theorem. And you can do similar heuristics for, yeah, so let me actually show you the heuristic for the shift. All right, so now you can ask yourself, what's the heuristic for this? Right? So let's do that in the case of phi 4. So the heuristic for t psi star mu equivalent to mu. And so in the case of phi 4, that's actually work of a master student of mine, who's Jacopo Carone, who is now just started to do a PhD with Hendrik. And so what's the heuristic there? Says, well, you have to compare the solution, right? Like if I shift the solution by psi, I can write down an SPD for the shifted one, and it's basically the same SPD as the original one, and I just end up shifting the nonlinearity, right? Well, and maybe the linear bit as well, right? And so it means that now you end up sort of comparing, you look at f of u minus f of u plus psi. Okay. And in the case of u cube, well, the u cubes cancel out, and so you get something like psi times u square, and then you get stuff with u, and then you get stuff with just psi. But in terms of regularity, the worst terms is the term psi times u square, right? Because remember, u square has regularity 2 times that thing, u has 1 times that thing, and so on, and it's negative. So the higher the power, the worse the regularity. And so then, well, the conjecture is that now, essentially, you have to replace, in your conjecture, the regularity of f of u by the regularity of that difference, right? Because now you're sort of comparing these two against each other, so the term with the u cube is sort of the same on both sides, and it's that term that counts. And so then it's basically the same thing, but you just replace 3 by a 2 up there. Okay, and then that's a theorem as well. Okay, so that this gives you the correct answer. Okay, so that here, so t star mu equivalent to mu if and only if. Now 2 times alpha plus gamma minus d over 2 plus 2 gamma bigger than gamma plus alpha, provided that you're in the regime where this is positive or you have local solutions and so on. Okay? And now you can even guess, like what's going to be the heuristic. I think by now it should be kind of clear how the game goes, right? So there's this Seagal's axiom story that I told you, right? By now you should be able to basically guess how the story goes here. So then the difference is going to be, well, you have to figure out, so basically this part of the story is the same. What's changing is that space here, because now you basically you look at the law of Z, but now you restrict it to a 2-dimensional or to a lower dimensional surface, and then you ask yourself, what's the Cameron-Norton space? That gives you a Gaussian measure on that lower dimensional, on the space of distributions on that lower dimensional surface. And then you ask yourself, what's the Cameron-Norton space for that measure? Okay? And okay, that's sort of depending on the situation. It might be a horrible calculation. But if you take, for example, in the case of the free field, if you take the free field in dimension d, the Cameron-Norton space is H1. And then if you restrict it to a t-1 dimensional hypersurface, the Cameron-Norton space is H1/2. So you basically lose 1/2 for every dimension that you go down. And then at some point you can't restrict. Basically, you can only go down 1 dimension. If you try to go down 2 dimensions, then at some point you find out that the free field cannot be restricted to a hypersurface of 2 codimensions somehow. But you can always restrict it to 1 with 1 codimension, and then it just goes down by 1/2. Right, so then it means that all the power counting is sort of the same, except that here you have not gamma plus alpha, but gamma plus alpha minus 1/2. And then you can do the same heuristic, right? And again, it gives you a conjecture. And there, so we have in the case of phi 4, with Fan Hao Kong, who was visiting EPFL last term, we had sort of the proof of one direction, at least, okay? But it's kind of clear that one can also prove the other direction with similar techniques. Okay, so now let me show you how to prove these kind of things. We've got 15 minutes. So, okay, so there are positive things you need to prove and there are negative things, right? And the proof is completely different for the two directions, right? So in one direction, you have to, right, like so there's the direction in which you want to prove that two things are absolutely continuous with respect to each other. And there, basically, the only tool that we actually have is Gazanov, right? So you need to find kind of a smart way of being able to use Gazanov, okay? And right, so proof of positive statements. So let me first, okay, so I show you how the proof by Jonathan and Tufik goes, and then we see immediately why it goes wrong. I mean, we know that in the case of Navier-Stokes, it has to go wrong because, well, the power counting for that proof is going to be exactly the power counting of that heuristic. So if the heuristic goes wrong, the proof goes wrong. But then we see how you actually fix the proof in the case of Navier-Stokes to push it further than the point where it's supposed to be able to apply, okay? So the idea is, well, you want to compare U to Z, okay? And so you want to do Gazanov, right? So now one thing you would want to, like the most naive thing would be to say, well, you just need to make sure that f of U is in the Cameron-Martin space of the noise, then you can do Gazanov, right? And then if you do the power counting, you find that in that case, you get something very similar, except that instead of having beta plus 2 gamma bigger than gamma plus alpha, you basically get something like beta bigger than alpha, okay? So that's essentially what this will tell you. And then you see that gives you a way too strong condition. You've lost one gamma, right? And you really need that gamma. I mean, gamma is like 1, and so that's, so that doesn't work. And so then the trick is to say, well, I don't care. You see, if it were the case that f of U is in the Cameron-Martin space of the noise, then you would have proven something much stronger. It's not just that the invariant measures are equivalent or the law at fixed time is equivalent. You'd have proven that the solutions on path space are equivalent. And that's a much stronger statement, right? You only want the marginals at fixed time to be equivalent. So then the idea is to say, oh, well, so since I only care about the marginal at some fixed time, then what I can do is instead of comparing the process U to the process Z, I just make up some fake process, V or whatever, which just so happens that at time 1, V is the same as U. But in between it does something else, and it's somehow closer to Z, okay, so that we can then apply Gazanov. And so how does that work? You just say, well, U at capital T is Z of capital T plus integral 0 to capital T, pt minus s, f of U as ds, right? So that's just my formulation, okay? And now the trick is to say, well, I can use the semigroup property. So I can rewrite this pt minus s as pt minus s over 2 times pt minus s over 2, okay? Can always do that. And then I can do a change of variables in s here, and I do the change of variables so that t minus s over 2 is equal to t minus r, okay? Which really means, what does it mean? It means S is equal to t minus 2 times t minus r, right? Which is 2r minus t. Okay, so you do that change of variables. And so then you can rewrite this as z of t plus now s equals 0 corresponds to r equal t over 2. S equal t still corresponds to r equal t. And then you still have a pt minus r now. And then it hits pt minus r f of u of, now it's not r, but 2r minus t dr. And then you say, well, now that's sort of the mild formulation of some weird equation, right? And so, right, so then basically what it means now is you just need to make sure that this guy, so that's still adapted because 2r minus t, it somehow, I mean, it goes in the right direction, okay? Like if r is bigger than, yeah. Okay, somehow, yeah, 2r minus t is always less than r if r is between 0 and t, somehow. Okay, and so this is still adapted. It's in some sense even more adapted because you kind of look further back instead of looking at the present. And then you can apply Gaussian. And so now now what you want is want that this is in L2 of time with values in H alpha or something, right? So that's the Cameron-Martin space of the noise. And now you see, now why does this gain us 1 gamma? It's because of this L2 in time, right? So now we're allowed to have some blow up, right? Because before all the arguments, we just use the things that are sort of uniformly bounded because everything is somewhat homogeneous and so on, so that doesn't make any difference. But now it's very time inhomogeneous and it kind of blows up, right? Like this guy is going to map everything into H alpha, right? So whatever, even if this is super irregular, this is still going to be in H alpha, right? Except that if this is too irregular, then it's going to blow up as R gets close to capital T, right? So then you have to ask yourself, like, how irregular is that guy allowed to be so that the singularity I get when R approaches capital T is still square integrable? And then you find exactly that condition up there, okay? So that shows you one direction of the proof, which sort of always works. Okay? And that's the one that was known for 20 years now. Okay? And so now how do you fix this? So what do you do in the case of Navier-Stokes? Right? Because that doesn't work, obviously. Right? So that would tell us gamma has to be strictly bigger than 1 in the case of Navier-Stokes. So how do you fix the proof? So fix Navier-Stokes. The idea is to kind of, instead of comparing the Navier-Stokes equations to the stochastic convolution, you compare, or instead of comparing, if you want that somehow fakeified Navier-Stokes to the stochastic convolution, you want to compare it to some equation that has the same invariant measure as the stochastic convolution, but is somehow closer to the Navier-Stokes equation already. Okay? And so then what you do is you say, well, you see if alpha was equal to 0, then, as I told you earlier, you actually know that the Navier-Stokes equations and the stochastic convolution have the same invariant measure. And that's because the Navier-Stokes nonlinearity preserves the H1 norm. Okay? Now here, the Cameron-Martin space now is no longer the H1 norm, but it's somehow the H, whatever, well, we had it somewhere up there, the H whatever, gamma plus alpha norm, right? And so now the idea is, well, fiddle around with the Navier-Stokes nonlinearity to find something which is very similar to the Navier-Stokes nonlinearity, but preserves the H gamma plus alpha norm instead of preserving the H1 norm, okay? And then of course, you know, how do you do that? Well, H gamma plus alpha and H1, they're sort of the same. You just hit the thing with some power of this, you know, absolute value of gradient operator, right? And so it means that if I actually conjugate the Navier-Stokes nonlinearity by the correct power of that absolute value of gradient, then I get something which preserves the correct norm, right? So you basically replace u grad u by, you know, gradient to the, and I guess if gamma is equal to 1, then it's really alpha, and then otherwise it's maybe, I don't know, something with gamma plus alpha minus 1, so alpha plus gamma minus 1 or something. So there's some exponent zeta, okay? So if you replace this by this, right? Then for this equation, the equation where the Navier-Stokes nonlinearity is replaced by something like that, and for that equation, it does actually preserve, it has the same invariant measure as the Ornstein-Uhlenbeck, right? And then, okay, so why would that help? And the reason why that helps is that now the claim is that if I look at the difference between these two, and I look at the regularity of the difference, then that's better than either of them, okay? And the reason why that's true is because of something called, because you have a sort of, there's something called the fractional Leibniz rule. And the fractional Leibniz rule tells you that, you know, say if zeta is between 0 and 1, it's almost as if you had a Leibniz rule, okay? So that was discovered, I guess, by Pons and Koenig and Vega or someone. I don't know, some time ago, 80s, 90s maybe. So this, by fractional Leibniz rule, well, it's more or less equal to, and I'm going to tell you in a second what I mean by more or less, to like this, grad minus zeta u plus u grad u. Right? Like if that guy hits that guy, then you just get a u. And what more or less equal means, it means again that like the difference between these two has better regularity, okay? And now you see, well, that's what we want. And now that one also has better regularity, because you see the problem here is that the regularity you get is one less than the regularity of u, is because that derivative hits u, right? But u itself has one regularity better than the nonlinearity, right? And so now here, well, that gradient zeta hits this u, but that's the u that has better regularity than the nonlinearity. And then this u now gets hit by a gradient, but with this minus zeta here, okay? And so this term here has also better regularity than that term, right? And so that tells us that the difference between these two terms has better regularity than either of them separately, right? And then the idea is, now of course there's a problem, is that this trick, as written, it really only works if you compare a nonlinear equation to a linear equation, right? So now you want to compare two nonlinear equations instead of comparing a nonlinear equation to a linear equation. And that's also what you want, right? Like for this thing about the shift here, that was the same thing, because you want to compare this equation to this equation, right? And there again, you want to compare two nonlinear equations instead of comparing a nonlinear one to a linear one. But then the idea is to say, well, if I want to compare two nonlinear equations, I can kind of make it linear by I interpolate the nonlinearities, right? I look at the one parameter family of equations, right? So I just introduce some fake parameter s, and at s equals 0, it's my first nonlinear equation. At s equals 1, it's the second nonlinear equation. And for s between 0 and 1, I just interpolate between the two nonlinearities in any sort of natural way, right? So you can figure out kind of natural ways of interpolating between them. And then you actually say, well, now what I want to do is I want to make sure I want to find a bunch of processes that now depends on s, and that are just such that at the final time, well, for every s, their law is equivalent to the law of the equation with the s nonlinearity, and at time capital T, their law doesn't change, right? So basically, I want to sort of interpolate in S and do basically a Gaussian shift for each of them, but now I have a sort of S-dependent Gaussian shift. And I want to find a Gaussian shift that basically cancels out the S variation of the solution at the final time, right? And then you do say, oh, I want that thing at the final time to be constant, so I want the S derivative to be 0. And then you write down what you get there, and now everything is linear again, because you sort of differentiate in S, so then everything becomes linearized. And it's just that these semigroups now are somehow the linearization of the S version of your equation, which you then, you need to do a similar trick, and then you integrate it up in S, and okay, you get some sort of an ODE in S for your Gaussian shift, which does the right thing. But then, okay, it becomes kind of fiddly and technical, but it's basically the same idea, but done in a sort of infinitesimal way that interpolates between the two nonlinear equations. Okay? And so then that kind of works. And then, yeah, so I think I'm running out of time. So that gives you only proof of one direction, right? So then you have to also show that if the heuristic breaks, then the things are actually mutually singular. So in the case of phi-4, for example. And so there you want to construct some event that kind of distinguishes between things, okay? And then typically the kind of events that you look at, say in the case of phi-4, is something like you take the fourth power of some fractional derivative of the solution. And then you sort of try to figure out how that fourth power is going to be singular. So it has to be some kind of weak power. And then you find that, well, if you stick in the Gaussian guy, which is obtained by solving the linear equation, then that weak power is fine. It's basically, well, it depends on the powers you take, but it behaves in a certain way. Whereas if you stick in the solution to the nonlinear equation, you essentially just say, well, I do a sort of first order Picard iteration. So I say my nonlinear equation is actually going to be of the form, the linear equation plus the term where I stick in here the linearized guy, and then plus a remainder, and the remainder is going to be even more regular in the case of phi-4. Okay, and then I'm saying that the effect of this term here, where I just put in the linearized equation, is to kind of mess up that fourth weak power. And if you sort of play with the exponents in the right way, you can essentially, you can construct an event that, detects that, right? And it's an event along the lines of you take that fourth weak power, you subtract some constant, some extra constant, then you test against the test function, and well, you take some regularization of the solution, you take the weak power of the regularization, you subtract some large constant, you test against the test function, and you ask yourself whether the limit of that thing, whether as the regularization gets removed, what is the asymptotic behavior of the quantity that you get? And you find that you get slightly different power laws depending on whether you stick in the Gaussian thing or you stick in the actual solution. Okay, and in that way you can actually distinguish between the two. Okay, but I think I'm out of time. Yeah, so thanks a lot.
Okay, well, thank you. Very nice. Are there any questions?
This comment you mentioned about the symmetric nonlinearity, something that should diverge doesn't diverge, that plays a role on that side you just described, on the negative side and up to the threshold.
Yeah, because you see, in the case of phi 4, with the sort of usual diagram notation, right, the solution, you basically, you assume the solution is of that form plus more regular, right? And then what you do is you look at some kind of fourth power of the solution, right? And so then the fourth power is going to have something like this, and then something like this, plus da-da-da. And then this you take some kind of Wick power, and then you use the fact that the expectation of this guy is going to sort of diverge, because there's going to be a contraction where you kind of contract these things like that, and that thing is going to diverge, and you know exactly which way it diverges, right? And then that's the thing you're trying to extract. So if you do the same for Navier-Stokes, well, here it would be quadratic, right? So there's a quadratic thing here, so then you try to do the same thing with a cubic thing, like that, right? But then you find that because of the sort of antisymmetry of the Navier-Stokes nonlinearity, the expectation of these things is always 0. And so then it doesn't really help. Right? And then you can try to do more sophisticated things, and of course we tried for a long time to show that they're singular, right? Because the conjecture was kind of that they're actually singular. And so you try more sophisticated things like that, and you find that there's always some cancellation, there's some integration by parts that makes things vanish. Right? And so you somehow never manage to detect the thing.
Can I ask one more quickly? Is there a connection between that story then and this other picture of supercritical and critical equations and studying the generator that can be done in this divergence-free setting, right?
No, here I'm not sure. I don't think there's anything to do with supercritical or critical. I mean, this is all subcritical. Right? So, and like in the Navier-Stokes case, you take alpha equal 20, right? I mean, there's nothing singular here. Okay. So in some sense, it becomes singular. So the reason why is, okay, so even in the Navier-Stokes, you can try to use things like this. And the reason why you could still expect that things like this could work is because what you do is you don't look at somehow the cube of the solution. You look at the cube of a sufficiently high derivative of the solution. And so then you make it a high enough derivative so that the cube is singular again, right? So that then this thing does need renormalization, even though the equation itself has smooth solutions. But okay, but it just doesn't work somehow.
Merci beaucoup pour votre exposé. For Navier-Stokes equation, from a applied numerical probability point of view, there are a lot of problems with the vanishing viscosity problem. So without modifying the convective term, is it possible to approximate the velocity and the pressure without information of acceleration?
I'm not sure what you mean. I mean, I don't think that this sort of trick would have any kind of relevance for looking at vanishing viscosity or something like that. I don't think so.
Because I see the trick to modify the convective term is the nonlinear part of the Navier-Stokes equation. For the vanishing viscosity problem, the convective term is so strong in comparison with the dissipative term.
Yeah, but you can't, you see here, we're allowed, like, you modify that, okay, so you see, so here we care about sort of these fine properties, so you care about sort of equivalence of measures or non-equivalence of measures. And so for these, in some sense, smooth bits don't really matter because like they always sort of differ by testing things at very small scales or something like this. If you do numerics on these things, I mean, the only thing you care about is the behavior on large scales, right? And that's the order 1 part somehow. So you're not allowed to just change the nonlinearity. Right? Like here, the reason why we're allowed to just change the nonlinearity is because then, we're able to sort of show that having this nonlinearity or this one is the same in sense of equivalence of measures of the solution, right? Like the solution at time 1 also with this nonlinearity is equivalent to the solution at time 1 to this one. But it doesn't mean that, like if you do numeric, if you look at that solution and that solution, they're not going to look the same. They're going to look the same in the sense that almost sure properties are the same. But if you look at the actual solutions, they're not going to look the same at all.
Merci beaucoup.
Any questions? Well, anyway, we are a little bit late. So propose to switch to the next talk.
Yeah.